নমস্কার, শুভ সন্ধ্যা সবাইকে। Good evening and afternoon, everyone, and a warm welcome to Kolkata R user Group's 7th virtual meetup. I am Somrit, the lead organizer of Kolkata R user Group, and by profession, I am a statistician and data solutions engineer at Atoras Research. Our group is very proud to be a diverse and inclusive community, welcoming individuals from all over the world with any backgrounds and any industries. So, whether you are a student, researcher, or professional, or simple curious about statistics, data science, and obviously art, we invite you to join our sessions, ask questions, and learn from each other. So, as promised, we are back again with another exciting sessions with our guest speaker today. So, if you missed out our previous recordings and previous sessions, so you can check out our YouTube channel. The recordings are available there, and please subscribe the channel and follow us also on our LinkedIn page. So, without further ado, let's welcome today's distinguished speaker, Mr. Soham Mukherjee, who will enlighten us on the topic Bayesian modeling with R stand. So, Soham is a PhD scholar at TU Dortmund and University of Tübingen. Let me know if I pronounce this correct because I am not sure.
It's Tübingen, but it's fine.
Okay, yeah, thanks.
Yeah.
And he develops Bayesian Gaussian process and latent variable models for uncertainty estimation in single cell biology. And he holds an MSc in statistics from University of Hyderabad. So let's welcome and start the sessions today. So welcome Soham and over to you. You can start.
Thanks a lot.
Let
Thanks a
me,
lot for the introduction.
yeah, let me stop
Yeah.
sharing and you can just start.
Yeah.
Yeah,
Just before I start, I mean, I don't
yeah.
know if this is permitted or not, depends on how the sessions are organized. I wanted to ask, like, from the audience, if someone wants to volunteer, that what is a statistical model in general? Like, very briefly, if someone wants to volunteer. It's also fine if no one does, because my first slide I would show it then. Anyway, all right. Let me share.
Yeah.
Yeah, it's visible, right?
Yes. Yeah.
Yeah. Okay. So, yes, and I will be speaking about like Bayesian modeling in general, and then of course because of the audience here, it would definitely have much to do with how to do Bayesian modeling with R and Stan. I just changed the title yesterday, so it's kind of kind of a little bit of a fault on my end, not from the organizers. So
It's okay.
because RStan is just one interface. I mean, we will see
Mm.
later on in the slides why I made this small change. Anyway, so let's start. Basically, statistical models. So what we generally see in our day-to-day life is that we deal with two different things. One is reality, and then one is model. And what we try to assume is that model is something that represents the reality as much accurately as possible. I mean, that's the goal. And what happens is there's this interconnection between reality and model. And what we see is that we have data that comes from reality, so like observations, and we put that into the model. When we fit the model, then we basically make some inference, and then we say something about the reality. That's how, like, in general, like in a very rudimentary way, statistical models work. Now, Bayesian statistics. I think, I mean, probably anyone who has seen statistics must be familiar with this expression. This is the Bayes theorem, where this is your likelihood. The probability of y given theta would be your likelihood. Probability of theta is known as prior. Probability of y is known as a marginal distribution. And then probability of theta given y is the posterior. I will go through all of these terms later in in the subsequent slides as well. And what happens in Bayesian statistics is that our method of inference is then based on this Bayes theorem that we just saw, and we try to estimate our parameters of interest. And like further, when we have that established, for further we also do data analysis methods when we have some available knowledge in of the parameter, which is basically our prior. We try to update it using the data that we see in the form of likelihood, and using Bayes theorem we combine that and put them together, obtain our posterior, which is the updated knowledge about the parameter of interest. So to summarize, the key components of the Bayesian of a in Bayesian statistics is prior, a distribution that expresses our previous knowledge about our parameters of interest. Likelihood, we assume a distribution of the observed data that we get from the real world. Uh, and then when we combine both of them using Bayes' theorem, we get posterior distribution, which is the updated distribution of the parameters of interest. By the way, feel free to interrupt if you have any questions. Yeah. Uh, so let's go one step further. We have something called a Bayesian model. I mean, of course, we have Bayesian statistics, and then what is a statistical model? I explain, and then let's look at a Bayesian model. So as we discussed already, a model is something that would represent a real event, right? And thus, keeping in mind the key components, that is prior, likelihood, and posterior, we should start by assuming a distribution that reflects our understanding of a parameter theta. Like let's call it theta, and that distribution would be our prior p theta. So if we take an example, for example, let's say we toss a coin, and we assume that uh, that the distribution of tossing the coin would basically be a like if we toss the coin once, it would be a Bernoulli distribution. Then it has a probability. This probability itself is a parameter of this Bernoulli distribution, and this probability p, if we know something about what kind of probability it might have, maybe it has a uniform distribution, right? Maybe it has a uniform distribution, and we believe that uniformly it should be zero point 0.5, like it's a fair coin. Then that's our prior belief. So that would be our prior distribution, p theta, which would be uniform. Uh, and then we have the data. So like if we repeat the coin tossing experiment multiple times, then we get the data, and that is our like we can assume that as like draws from our likelihood, and like we assume that this data follows some distribution, that is our likelihood, and we call it probability of y given theta. But we combine that with likelihood and prior, and then we get our posterior p theta given y, and then we can like do other downstream analysis and then finish our inference. Uh, so let's start by looking at a very simple model. Let's say we are interested in like income of people in a city. Maybe it could be Kolkata, right? We let's say we would like to know if the educational degree or popularity of institution might affect the income of an individual more. Like I don't know if it is correct to like name an institution, but let's say institution A and institution B. A is a bit more popular in some with some metric. People might say that if you get your degree at A, then you will probably end up with a higher income when you get a job, something like that, right? So with this setup, we can denote this model as something like this. I mean, I'm assuming people are familiar with linear regression, where then our y, our target variable, would basically be the income of the people in the city. X1 and X2, let's call it X1 be the educational degree. I mean, let's say we assume that someone has 0 degrees, so basically did not get school level education, could have 1 degree, just pass the school level, could have a BSc, could have a MSc, could also have a PhD or some other multiple degrees, could have 2 master's degrees, something like that. So the number of degrees could also would be reflected, and based on that, one might be interested in knowing that if I had one more master's degree, would my income be more when I get the same job, right? So X1, let's call it the number of educational degrees our samples have. X2, we can say it's the popularity of institution based on some metric. Um, like I don't know what kind of metric, one arbitrary metric. And then in this model, of course, we also have the random error epsilon, which has some assumptions. I'm assuming everyone's familiar with that. Then we have the parameters here. The parameters here are in like necessarily the beta naught, which is intercept term, beta 1, which denotes the weightage of the number of educational degrees covariate, and beta 2, which expresses the weightage of the popularity of the institution. So in order to answer this question, if educational degree or popularity of institution might affect, how it might affect positively or negatively, if if the educational degree or the popularity would affect more or less, something like that. What we would need to do is we would need to estimate beta 1 and beta 2, right? Once we get that, we can then make a statement about how X1 might have affected the income, which is Y. X2 might have affected the income, which is there. And that's our purpose at the moment. Let's call it that. And I would request to like keep this one in mind, because like later on in the slide, I'm also, when I'm showing the R examples, I'm using this very same example so that we can have a nice continuity in the full presentation. So, so here it is, our simple model. And as I said, this is a Bayesian model. So what do we need to do first? What we saw is that we start by assuming a prior for our parameters. Here our parameters are beta naught, beta 1, and beta 2. Let's say, I mean, there is a beta naught missing, but let's say we assume all of them follow some normal 3 comma 3, where I'm assuming 3 is the mean, and the other 3 is the standard deviation. Um, don't ask why I assume this. Just consider this is an arbitrary assumption, right? I mean, if we go into the discussion of how to choose priors, there's a huge literature uh, and like more ongoing work going on. So that's a entirely different set of presentation. One can fill a full day workshop with that. So if we assume that this our parameters follow a normal 3 comma 3 distribution, it would look something like this, right? And once we have fit the model based on some data that I have generated, like behind the scenes, I will show that data later on, then what we would have, we already know this is our prior based on our assumption. And once we fit the model, we would see something like a posterior for our beta 1 and beta 2, right? And as you can see, the family still remains the same. However, if you see the x-axis, things have changed a little bit. While it was centered around 3 before, for beta 1, it is now more centered around 0. And for beta 2, even it might be centered around 3, but the variance has now changed, which means that the prior has changed to the posterior. That means that the data has had an effect and the model has learned something from this data. And that is exactly how the updating of prior from prior to the posterior works in case of Bayesian models. Yeah. So what we're looking for is to obtain the posterior, right? Now, there are some issues here, and these issues we will address by means of Bayesian sampling. Let us revisit this Bayes theorem expression. We know we have our likelihood, we have our prior, we have our posterior, and then we have our marginal. And this marginal is the nuisance, is the issue here, because this marginal, if we break it, like if we open it up, it would look something like this, which means it depends on the likelihood, basically on the joint distribution of your likelihood and the prior. And this this in many cases is intractable. So you can't compute this you can't solve this integral. When you can't solve this integral, the previous equation it does not make any sense, because then you won't have any posterior. So how would you overcome this challenge? Because this is a challenge that you will see more often than you would expect. So this challenge is solved using by sampling. So what you do is you try to bypass the computation. So you don't try to compute the posterior. You try to sample instead. You try to sample from the posterior, which effectively would have a similar effect, because if you have large enough samples, you are basically saying that you're having asymptotically unbiased estimates. So if you had computed the posterior, that would be great, but you can also have good number of samples from the posterior and still make the same level of inference. So as I said, this in many cases this marginal is intractable. So a solution is then you sample from the posterior distribution without needing to specify a compact form. And this method that you would need, one of a family of such methods are known as Markov chain Monte Carlo, MCMC. Probably many people have heard of that. And like what that says is, like, you can see two parts in this. One is Markov chain, and Markov chain is basically a stochastic process which is defined where the nth event only depends on the n minus 1th event. And Monte Carlo sampling is basically the technique where you say that you can you can get asymptotically unbiased estimates just based on the sampling, instead of like computing the exact uh, exact compact form of the posterior in this case. Yeah. So now there are different types of MCMC, because MCMC is a very huge, it's a huge class of algorithms there. One of the earliest and probably the broadest class of algorithms is the MH algorithm, or the Metropolis Hastings algorithm. First developed by Metropolis et al. In 1953, and then improved and, well, the current stage by Hastings in 1970. What it does is that it shows you, it starts with a proposal distribution. It asks you to specify an acceptance and rejection criterion, and based on that, you would try to reach your posterior. There are a lot of terms here, and I will actually explain it in a bit. So I would request your patience. Like some other forms of, also from the class of MH algorithms, but some other variations of that are, let's say, Gibbs sampling. The, these were developed in 1971 and 1984. Gibbs sampling depends on sampling via conditional distributions. So you would basically condition upon your observed data and try to sample from try to sample your parameter on the first step, and then you condition upon your previous step value of the parameter, and then try to sample in the next step. And then there is a much more contemporary Hamiltonian Monte Carlo, which is the HMC algorithm. And this algorithm, uh, they have like much different properties. It also has a huge literature there, and I think it would be a bit brave to go into what these different types of algorithms would look like in this talk. So I would just give a very brief overview, and then I would ask you to focus on this HMC, because that is what we would need in the later parts of the slide. So the key features for all these algorithms, and in general also for MCMC, is that we start with an initial value, and we then set up an acceptance rejection criteria. So it is almost like saying that, let's say we are having a conversation. Let's say I am person A, and someone from the audience is person B, and I'm trying to say that I have this idea that this person B would know or would have samples from the posterior, and I would need those samples from the posterior, and I would set up a condition, and this person B would throw me samples, and I would actually say, yes, this sample looks good. This sample might be from the actual posterior. And then the second sample comes, and I would say that no, this sample does not look so good. So we reject that sample. Give me another sample. This is exactly how the dynamics works. And you repeat this step over n number of times, and those are like iterations. And then you try to gain some sample, and you say that this is the set of sample from this posterior distribution that you were looking for. So you would have to iterate this step over multiple times, and then you obtain these samples from the posterior distribution. And that's how you are getting your asymptotically unbiased estimates from the posterior distribution. Right. Now, since this is an algorithm almost always comes with some kind of convergence criterion. And your models also need to have this convergence. So if I am, and in this case, what does convergence mean? This is a plot that you will probably see, I mean, almost every time you run a Bayesian model. Yes, probably every time you run a Bayesian model. What this plot shows is basically like two different Markov chains. And as you can see, there is a very clear stationarity uh, that is being represented here. And this is one of the assumptions of a successful MCMC process. The chains need to look stationary. Not only that, you can see that there are two chains, and these two chains seems to have mixed quite well, reasonably well. What it means is that I started asking, let's say, two people, right? Two people, I started asking about samples, and after a while, they started to give me like similar, reasonably similar samples, and thus I can conclude that I started from two independent points, but I reached at a sample that both of them agrees to. So that there is reason for me to believe that is actually samples from the posterior that I was looking for. So this mixing means that the chains are agreeing on the value of the posterior, like on the samples of the posterior. And on the x-axis, you can see the number of iterations. Sometimes what happens is that these chains do not agree. So it would look something like this. And when this happens, then you basically say that your model has not converged. There could be multiple issues why your model has not converged, but when this happens, basically you cannot use any estimate from that model because those simply can't be trusted because the chains have not agreed. And then you would need to refit your model. You would need to fine tune your model. You would need to uh, like there are multiple things how you can debug your model. It might be some very fundamental mistakes in like some assumption of the model itself, some model data mismatch, something like that. Multiple issues, but those are more on the model debugging uh, sides. Right. So when you have okay, so this goes for model convergence, and these kind of plots are known as trace plots, and as I said, you will be looking at them quite often, like every time you fit a Bayesian model. Right. Then some terms that are needed to like fit a Bayesian model. The first is iteration. We have discussed this. Like iterations are the number of times the algorithm tries to sample from the posterior. So the number of times you actually try to get a sample from the posterior distribution, and that would be your iteration. Basically what you say is that you would after this number of iterations is over, you would actually stop the algorithm and then you would check the quality of your samples. Chains, the number of Markov chains. In the previous trace plot, you saw two Markov chains. You can also like have three Markov chain, four Markov chain. You can have 100 Markov chains if you like. They are like as you these Bayesian method, these Markov chain Monte Carlo methods, they are computationally expensive. So you would ideally need more than one chain, but you would also need to restrict yourself to not have more than, like, not have too many chains. So like a suggested would be, like, suggested upper bound could be 4 chains, I think, like especially when it comes to Hamiltonian Monte Carlo. And I mean, when you increase the number of Markov chains, you basically gain more confidence on the quality of your samples, and that's it. Initial value, you need to specify a starting point of these chains. If you don't, I mean, the algorithms are uh, designed so that they have their own default value, but it's nice if you know some initial value. Could even be a very uninformed initial value, which might be 0, something like that. And then there is this warm up. Warm up is basically when the initial samples are discarded. The thing is that with these chains, and I'm going to go back to this slide once more, where when you see these Markov chains, you're not seeing uh, the exact point from which it started, right? Because you would need to the allow the algorithm to get used to this to get used to be to allow the algorithm to be closer to the posterior distribution first. And when they are not close enough, there is no way that like any number of chains would agree. And you would not want to like include those values into your sample, because if you do, then you will actually never see the mixing of the chains. So instead what you do is you discard the first few uh, samples, and then after that you consider what you get are basically the samples from the posterior. And this first few initial samples is known as the warm-up samples, or the just warm-up. And you need to specify this when you're running the model. uh, Now there is another sampler which is known as no U-turn sampler. It was developed by Hoffman and Gelman in 2012. And this is basically based on this Hamiltonian Monte Carlo. And this is just a more user-friendly version of Hamiltonian Monte Carlo, because Hamiltonian Monte Carlo is a little bit uh, I wouldn't say it's difficult. It's just it has so much literature covered, and there are lots of flexibility in model tuning that it is not very beginner friendly kind of sample. Like MH algorithm is much more user friendly, but so no U-turn sampler, it's much more user friendly. And when you're using Stan, you would like basically be using this no U-turn sampler, and thus I'm introducing it here. The advantages to this no U-turn sampler is it minimizes autocorrelated samples and are great at model convergence, right? And since I'm on autocorrelated samples, there is also this notion that you would, when you see these samples that you get from the posterior distribution, you would need them to be independent samples, because otherwise, if they're correlated samples, then it does not make any sense uh, to consider, like, to infer anything about those estimates. So if you, like, let's say you have an estimated mean of a posterior distribution, and if the samples themselves are not independent samples, then you can actually not provide good inference, or like very realistic inference without like additional properties, additional theorems that are in play. So this sampler, what it does is that automatically it minimizes these autocorrelated samples, and like also provides great model convergence, which means you also need to not use too many iterations. Uh, the disadvantages there is that this is one of the slowest algorithms per iteration among the Hamiltonian Monte Carlo class. So like MH algorithm and Gibbs sampling, they are quite fast. However, like from my experience, and probably like for anyone who has used them, I think you would almost always need the total number of iterations as like something like, I mean, at least 10,000. And I think having 50,000 iterations or even 1 lakh iterations is not unlikely, like for some complicated models. Compared to that, in this like Hamiltonian Monte Carlo or this no-Newton sampler, you would only need an iteration number of 2,000, and that's it. So even if it is a slow algorithm, it's still like, since you're not setting too high number of iterations, you actually are not losing too much here. Like on the other side, you get very high quality of samples. Stan. So with that in mind, we can start with what Stan is. So Stan is basically a platform for statistical modeling and Bayesian inference. All of this that we discussed thus far is something that you can already do automatically with Stan. This gives you the environment to specify the statistical models. You will see how I specified that simple model example that we discussed at the start, and we basically would see that it's quite easy to specify all of these statistical models. And as I said, it relies like this Markov chain Monte Carlo sampling flavor is basically based on this Hamiltonian Monte Carlo and this no-Newton sampler. And like this is how Stan as a probabilistic programming language would work. This is available in R, and if there are Python users, also in Python. But primarily, this was designed for R. And I think I spoke to some of the developers of Stan, and they actually they confirm that uh, it's mostly useful for our user bases because they haven't yet finished migrating it towards Python, and they are constantly like pushing updates focused more on R. And if you're interested in more details, tutorials, and all of these things, they have a very good amount of literature in this mcstan.org website, and like they have like really good handbooks to like get you started. And I think it's quite easy to get get you hands on with this probabilistic programming language. So and then next is RStan. So Stan is a standalone probabilistic programming language, and thus you need to connect it to R. And this connection is done by RStan, which is the R package. And this is basically the R interface to Stan. And using RStan, you basically what you do is you translate what you have specified as a statistical model in Stan language, and then you fit them using R. And after model fitting, you get access to all of these model inferences, these trace plots, these model MCMC diagnostics that you would need, the posterior samples, model summary, and all of these things. Uh, Sort of automatically, like just few lines of code. You just need to call some functions, and that's it. And you just get it for like for cheap. When you install RStan, it also depends on like these few R packages. Basically, Stan is based on C++, so it needs all of the dependencies that R would require from C++, and Stan would require. But you don't need to worry about this because once you install RStan, they just get installed automatically. So I don't think there should be any difficulties there. Um, yeah. So now let's look at a typical workflow. So how would you go around setting up a model in Stan and then use RStan, and then you would do your Bayesian inference, right? So you would start by, as I said, you would start by specifying a statistical model. You would write that model in the Stan probabilistic programming language. And so it is recommended that you open a .stan extension file and write your statistical model there. I will show you how you can write it in a few slides. Um, and this, if you're using RStudio, you just go to the file and you can see lots of supported files. There would be one Stan file, and you can open it, and there you can write it. You can also use an inline text inside R, and you can also call this stand model, but usually it is recommended that you just use a separate stand file. It is much more cleaner, much more easier to maintain. If you're building packages, then it is absolutely recommended that you have a separate file for your stand model, a separate file for your R script where you compile the stand model and then fit your Bayesian model and get your outputs and all the downstream inference tasks that you have plans to do. So after you have specified the statistical model, then you prepare your data as a list object in R. I will show you again, of course, how to do that. Then you would fit your model in R using R stan. So you need to call the stan function in R and just compile the model, and it will then provide you with a model object. And then using that model object, you can perform the convergence diagnostics of the MCMC chains. You can get your posterior samples. You can get your estimates. You can get your standard errors of the posterior samples. You can get credible intervals and lots of other different things that you might need for your research, for your in general from the Bayesian model that you might expect in general. Yeah. And yeah, as I said, this you conduct all the downstream inference stuff with your posterior samples. So like step one, you simply you simply open a stand file, and this is where I just had my simple stand model. The simple model is basically the same one that I just explained in the example, and you write it down there, and this would be a stand file, right? And in the stand file, in the statistical model, there are three different blocks at least. So these are three different primary blocks. One is the data block. This data block is where you declare what kind of data the your statistical model would expect, and this data, like all of them, you need to provide when you specify your when you try to call this statistical model using rstan in R. You would also need to prepare this data so that you can pass it on through the rstan package, and your statistical model in stan can actually access it. Then comes the parameter block. This is where you would explain your parameters. As I showed, for this model, your parameters are your intercept, beta 1, beta 2, and sigma. The sigma comes because your epsilon, remember the epsilon? The epsilon is, I assumed epsilon is follows a normal with zero mean and sigma square, and this is where the sigma comes from. So then you would have to declare your parameters, and these in whatever is in this parameter block would get estimated in terms of samples. So MCMC, what it would do is or STAN, what it would do is they would provide you samples for anything and everything that you declare within this parameter block. Then comes the model block. In this model block, you specify your priors and your likelihood. So remember again, the model. The model was basically y equals beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So you have your beta naught, beta 1, and beta 2. And in this case, I use intercept, but just consider it as beta naught. So I would need to set priors, and my priors, as I assumed, that they were normal 3, 3. So I have specified our intercept beta 1 and beta 2 are being specified as a normal 3, 3. And then I would need to specify the likelihood distribution, and this is something the y follows. It would be a normal distribution because my epsilon follows a normal distribution, with the formula intercept plus beta 1 times x1, beta 2 times x2, and then we would have the sigma. No questions, right? Okay. Right. So step two. Then comes then you would have to once you have specified all of these things in your stand file, you don't need to touch your stand file again unless you want to edit it. Like you want to, uh, you know, make things more
Soham,
flexible. Yes.
hi. Just I have one question. Hi,
Yes.
actually, I work in MCMC, so that's why I got this is a really nice talk you are giving. This is
Yep.
helpful a lot. So the question is like, in the previous slide, as you specified that yes, yes.
Yes.
So one has to specify the data block, parameter block, and the model block. So
Exactly.
yeah, yeah. So when I tried this data flow, actually this data
Hmm.
block inputting,
Yes.
so I feel that there are some like there are not so developments over like dimensional type data. Like since these kinds of, as you mentioned, that these data types are actually some
Hmm.
vectors and even kind of matrices. But
Yes.
if someone wants to work with like functional data with like tensor type objects, like if one
You,
works with the brain
yes.
MRI data,
Yes. Yes.
so I don't know actually. So can you yeah, you know that that kind of data structures can be used in this framework,
Yes.
or
Yes.
one has to
Absolutely.
develop those
No, no, no,
things?
no. You can specify it. I mean, as I said, this is
Okay.
only a simple model, right? So, for example,
Mm,
I am in my model, like in
mm,
my
mm,
actual research, what I'm doing currently,
mm,
I'm also like my Y. Like
mm,
I'm
mm,
not showing the example at the moment, but my Y
mm,
itself is
mm.
not a vector; it's a matrix. So you can
Okay.
specify it as a matrix. Then you would
Okay.
have to specify matrix as let's call it n cross d. Then it would be like instead of a vector, you would specify it as a matrix n comma d, something like that, right?
Okay.
If you
And
want a 10,
the set of parameters also can be like matrices, the
everything,
real matrices, every.
everything,
Okay. Okay. Okay.
every
Okay.
one of them.
Okay.
Uh, f- yeah. So you were speaking of tensor. In case of tensor, it would basically in this case would be an array. So you can
Hmm.
specify it as an array, and then you can specify its dimension. You can actually find all of these data types that Stan can accept in this. I mentioned this mcstan.org. So they have a
Okay.
very nice handbook, and there you can find out all of the data types that they can accept, right?
Okay.
Yeah, and that is exactly why I said this is a very flexible way to specify anything that you might think is applicable for your specific research purpose or project, whatever.
Okay. Okay. Okay.
Yep.
Yeah. Thanks. 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 Thanks
Right.
for yeah. Yeah.
Any other questions?
No. No. No.
Okay. Like anyone else? No. Okay.
Yes, someone
Yeah.
raised hand. So yeah,
Yes.
can you speak or you can type your question in the chat section, whatever you want.
Yeah. I mean, I can't see, so someone would have to then read or just.
Yeah, I will read out. Yeah, yeah,
Yeah.
sure.
Thanks.
Okay, another question was asked in the Q&A section. That is,
Hmm.
how can prior distributions influence the posterior in Bayesian modeling?
Oh, that's a classic question. In so many different ways. Uh, so um, can I take that question later on? Because I think it would be better if I go back to the slide, like
Yes,
the
yes,
slide
yeah.
where I have the Bayes theorem, right?
Mhm. Yes,
So
yes,
like
sure.
whoever asked this question, I would request to be a little bit more patient. So I think
Mhm.
I only have just not so many slides after this, and then I will definitely address that question. Is that fine?
Yes, yes, I think
Yeah,
we are fine with that.
good. Okay. Um, right. So then I'll just proceed. And again, as I said, feel free to interrupt me and if you have any questions. So yeah, so once you have done specifying all the specifying your statistical model in the stand file. Now you would just do everything in R. So you would call your library rstan, and this is where I'm preparing my data. This is a dummy data, by the way, like something that I just did it probably, yeah, like 2 days ago, something like that. So I took out a sample size of 50. I specified my y to be some normal distribution that would sample 50 samples with some arbitrarily chosen parameters, x1 also something like like a categorical variable, and then your uniform like x2 as some uniform variable. Like none of these choices have anything to do with like any sense at the moment. This is just a simple model to demonstrate how a standard model might work. And as I said, that you need to prepare the data that you would then pass to the stand model. And this is where the things need to be, you need to be very careful, because then you need to declare a list where you specify all the variables, sorry, all the um, how would I say, all the quantities that you have specified in the data block in your stand model here in this list. So I will just go back one more time. See that I have declared the sample size n, the data y, the covariates x1 and x2. And I would need to then specify what n is in this data block, what y is, what x1 is, and what x2 is. Once you're done that, you then need to pass it, and you need to fit your model in R. And this fitting the model, you simply call the stand function. You have your file. I saved it as a simple model.stand file. You specify what file it is. Previously, my data list was the simple model data. And then remember those terms that I said that you would need for like this inference. You need to set up, you need to specify how many iterations you would do, how many chains you would, Markov chains you would like to run, the number of warm-up samples that you would basically discard, some initial values. I just chose 0. It is completely uninformed. And the scores is basically based on like how many cores you would need to run these chains. So automatically you can parallelize. So if you specify I need 4 chains, and I have 4 CPU cores in my machine, local or cluster, whatever, then what it would do is it would parallelly run these 4 chains in like with these 4 different cores, and your model is basically then running a bit like much faster. Otherwise, if you don't specify these cores, it would just take the default as 1, and then it would sequentially fit each of these chains. So like first chain 1, chain 2, chain 3, and chain 4, and automatically then the time increases. And this is how we would fit the model in R. Once we have fit the model, then it is now time to diagnose the chains. This trace plot function also comes with RStat. Simply call the trace plot functions and put in this model fit object, and then it would give you something like this. And you have as you can see, that the chains have mixed pretty well, which means whatever comes out of this model we can trust, like the estimates, something like that. And then once you have that, you can also call this print function of this model fit, and then you would see something like this. People who have been working with linear models, this LME syntax, they probably are very familiar with this kind of output. What you would see is basically you would have this mean, which is basically the posterior mean of the parameters. Here you have intercept, beta 1, beta 2, and sigma. You have the standard error of the posterior mean. You have the standard deviation, and 2.5, 25, 50, 75, and 97.5. These are your credible intervals, like with the posterior credible intervals. For now, that's it, because in the next slide, I would actually show what NF, which is basically an effective sample size, and R hat means. Any questions up till now? Okay, so you saw the trace plots. This is the trace plots are a wonderful diagnostic, but sometimes you might also want something more numerical, and that numerical convergence measure is basically R hat, and this is basically a measure that is based on the ratio of within chain variance. So like you have your chain, so the chain variance that you have for each chain, and then between these chain, what is the variance that you might have. I mean, it's a bit more complicated than that, but I think as a proof of concept, that should suffice. And that gives you a nice understanding of how well the models have converged. And then there's effective sample size. This is basically the measure of the amount of independent information is in your sample. So the measure of independent samples that you might have. If you want like if anyone is interested in what they actually are, like the formula, the math that is there, the full definitions, I would definitely encourage everyone to look at this Aki Vetari's paper. He's one of the stalwarts in Bayesian modeling and MCMC at the moment. He's based out of Aalto University, and his paper in 2021, I think it's in Bayesian analysis. So you can find it there, and yeah. So then you would basically see, and yeah. So uh, in terms of R hat, you would basically want this to be as close as possible to one. Sometimes your models are a bit too complicated, so you might not get like exactly one, but you might get something like 1.0203, something like that. It is generally suggested, and you would find these things mentioned in the paper as well. It is generally suggested that the R hats should not exceed like 0. Sorry, 1.05. Anything beyond that is fine. In cases of very complicated models, I think sometimes you can also take a much more relaxed upper bound of 1.1, but anything beyond that, then things get really bad. And you would also see that in the trace plots where the chains will not be mixing good enough, and then you would start to question what the estimates, and probably would need to refit the model, do some model tuning, and some more stuff, and like some model debugging if needed. I don't know, things like that. Right. Uh, Once all of these are done, then you have your posterior samples. Then what do you do? Maybe you have like quite a few different, you have 2 or 3 different models. Then you would probably want to know what to do with like all of these models. You would probably need to choose one. And then comes the topic of model comparison. But I will not focus on model comparison in detail, because again, this is another another rabbit hole that one can go into. Like all of these are different sessions that one can do. Like it's a whole coursework, I think. And so like for for uh, for this setting, on a very brief note, I would just say that you can primarily look at error-based measures, root mean squared error, or uh, mean, approx mean approximate error, something like that. Well, sorry, mean absolute error, and as I said, as you know probably already, these errors only make sense when you have some ground truth available. Sometimes you don't have them, so these errors then does not make much sense. You might then want to do something like a cross-validation method, where you have like leave one out cross-validation, where what you do is basically you take a single a single set of samples out from your data, fit the model on the rest, and then try to predict that sample and see predict that sample, and then you repeat that by removing one sample every time and refitting the model, and then at the end you compare how well your model have predicted uh, the samples that were left out, and that gives you a good understanding of how well your model could predict, even if the sample was not seen, even if the data was not seen, something like that. So that's also a good measure of good measure of comparison, of model comparison. And yeah, you can definitely read again Aki Vetari's paper here. Like there are much more like in-depth discussion about what LuCV is, or like even more extensions of LuCV. Right, and this is where things get a little bit more interesting. All of these things that I just showed you, you can actually do everything in a much more simpler way. You don't even need to look at Stan. You just need to look at this R package by Paul Berkner. He's basically my supervisor. Uh, there is this package VRMS. I don't know if people used it. Maybe people also know about this package already. In the background, it still runs Stan, so it will also install like all the dependencies that I mentioned for Stan. But if you are not, if you don't require the flexibility of writing your own statistical model beyond what BRMS provides you, then you might even just look at this, because you get everything that comes out of comes out of the statistical model that you might have specified in Stan and fit in R using R Stan and things like that. And I think it makes the process a much more streamlined, much more cleaner, and you will basically see why I say all of these things. So what BRMS does, and you can of course see all the references that I have mentioned. It is basically a package for Bayesian GLMs using Stan, and it is more true for a much broader audience where the Bayesian modeling is much more accessible. You can also specify very complex models here, but only up to some extent. And in most cases, I think regular users would never need something more. Some very high level, like high level, not in a sense like very good. It's more like niche researchers might need some very curated models. Then BRMS might fall a bit short. For example, in my case, I don't use BRMS. I absolutely need to specify my own stand model, and yeah, BRMS does not support that kind of stand model yet. And then you also have, like, it's a GLM, so you have support from wide range of families. Not only just GLMs, it has support for splines, ridge regression, lasso, uh, for mixture models, Gaussian processes, something like that, like Gaussian processes in a very basic, like standard Gaussian processes. uh, and then it allows you to specify your priors. Also comes with post-processing tools like all of the trace plots and the things that you've seen, conditional effects, marginal effects, all of these things. And if you want more details, of course, please visit the Vinet pages. You would find lots of tutorials on how to use. It's, I think, very easy to get started. And one of the big reasons for that is because BRMS uses the exact same syntax of LME4. And so in R, you would basically, if you are using BRMS, you have your data, you specify your priors. You don't even need to specify your priors if you don't know, because BRMS does that automatically for you. It has some default priors that it would do. If you don't know anything about your prior, don't need to specify anything. You fit your model as you can see. You have syntax that is very similar to LME4. If you had, I don't know, like random effects or mixed effects, you can also specify it by the exact same way you would have specified it in LME4. Like, you have plus, let's say if X2 was a random effect, then you would basically specify it as plus first parenthesis one given X2, something like that. I mean, people know it already. You give your data, you specify the general conditions, general terms that I already specified in the Stan, and then simply let the model run. And once the model runs, you can call the summary, and you would see something like this. Again, this is very familiar to, like, the LME4 package. Also in Stan, this is quite familiar. And you get your estimates, you get your error for your estimate, then the 95% lower and upper bounds of the credible intervals. You have your R hat. Uh, you basically also get a breakdown of your bulk effective sample size and tail effective sample size. It basically means if you have, like, how much mass would you have in the tails of the distribution and the uh, central part of the distribution. And then of course you have some, like, it's arranged in a way so that it is more generalized in cases of GLM. but for this simple example doesn't make too much difference. And of course, you can also print, like you just use plot M1. M1 is the model, and you would see something like this where you have your trace plots. And not only that, you also have the posterior distributed density plots for all of your parameters. And yeah, and based on that, you can already have a good understanding of what you have fitted for your model, and what are your posterior distributions, the samples, the convergence diagnostics, and like all of that all in one place in one plot. And I think you can already, it's kind of ready to use even in good reports, and like in scientific reports, and I don't know, like your master's project, something like that. So yeah, I guess that's it from my side for now. You can, like, if you have any questions, of course, please ask me. And let's say you have questions afterwards, after the session is over, feel free to contact me using any one of these emails. The second one is my personal email, so it's like even when I'm not when I go away from TU Dortmund, I would probably not have access to the first email. Then I would have access to my personal one. Uh, as I mentioned, these links, if you are interested in further reading about these things and using them in your day-to-day lives, I would really encourage you to look at them. They have very nice tutorials and very nice resources to get you started in I think you can actually get started in like 1 or 2 hours of reading. But if you need to like really get good at that, then you should spend a little bit more time. And if you are actually more serious about how things actually work, then you should also consider adding, like, reading these additional like reading materials that I mentioned on Bayesian inference. The first one is basically I'm basically I provided the links where you can find the books. The first one is Statistical Rethinking by Richard McElreath. I don't know, maybe you have heard of this book. It's a very easy to read book on Bayesian inference. The second one is basically the Bayesian Choice by Christian Robert, and the third one is the Bayesian Data Analysis by Andrew Gelman and Aki Vehtari. And if you need to visit our lab websites, these are there. And yeah, my colleague also taught his lecture on Bayesian data analysis this semester in my university. So I got inspired and took a couple of images and some points for my slides as well. And he also allowed me to use them. So yeah, so that's it from my side. Questions then, perhaps?
Yes, thank you, Soham. This is a
Yeah,
really wonderful session, and I
pleasure.
really enjoyed it. I think all of the participants has enjoyed. So next one is, yeah, any question do you have? Anyone?
I mean, I'm gonna minimize, and if I
Yeah.
need it, I should probably turn on the light as
Huh.
well.
Huh? Mm, no question from. Okay, so that one you have already answered, right?
There was another question in the chat, right?
Uh, okay, no, there is nothing.
Like someone, I think, asked about how the priors affects.
Oh, yeah, yeah, that is
True.
actually in Q&A section, not in the chat section. Yes, yes, right. Yeah, so
Okay.
how can prior distributions influence the posterior in the
Wait.
modeling?
Yes.
Hmm.
Let me actually share it again. I completely forgot. Sorry.
Okay.
Right. So, uh, here is you have your prior as p theta, and then you have your likelihood, right, as p of y given theta. So if you say that your data does not have enough power, then, like, when I say enough power, it means basically enough information. So it's basically a very general data. So like, okay, how would I explain it in an example? Yeah, okay, how about this? Let's take this example of coin tossing, right? You had your prior about this probability of getting a heads or getting a heads, and your prior probability or your belief was it is a fair coin, so it is just it is 50%, right? Let's say you have repeated this experiment, you know, uh, I don't know, 50 times, and you have recorded the data, and if your data, let's say, did not, let's say, showed that it is indeed a fair coin, then your prior does not change, right? Your posterior is basically almost same to your prior. However, if your data actually, let's say you were very unlucky and you never got head, and then your prior would be like, when you combine it, your posterior would be very different than your prior. Your probability would be shifted from zero point 0.5. Similarly, on the other hand, let's say your prior was extremely informative, right? Let's say you had a belief that your prior was um, something like only 10% of the tosses would be heads. Then if you don't have enough data that would actually allow you to go to the true posterior, your Bayesian model would not be able to counteract the effect of the prior. Your posterior would still be
Mm.
similar to the prior, something like that. Does that make sense? So like so depending on the strength of your prior, your posterior like depending on how informed your prior is, your posterior would be different. And what happens is that if you have very large sample, then your prior almost never makes any effect, because you have so much information that your posterior is basically just informed by the likelihood, and that actually then your posterior estimates actually converges to the frequentist maximum likelihood estimate. And yeah, then you could say that the frequentist maximum likelihood estimate is kind of a specific case of the Bayesian specific case of the posterior estimate, just when you have large enough samples. So whoever asked the questions, just let me know if that was sufficient, or otherwise I can explain more as well if you want, if needed. Yes, no?
No response yet,
Yeah,
so
okay.
I think
Well,
it's okay.
right.
Yeah, I Soham.
Yeah, hello.
Yeah, I am Sudhi here.
Yeah.
So just I want to know if you're aware of about the clinical trials. So we have the step discarding, right? Sample discarding something. Warm up step we had mentioned, right?
Yes.
So how it will work in case of clinical trials? For example, like in oncology trials, we'll use Bayesian models. Just I want to know how it will apply the warm up step.
It is same. I mean, it does not have to do anything with the specific use case, because like, so your model would change, of course, based on your field, right? For example, if I'm using some if I'm trying to analyze some trading data, I would probably do some stochastic volatility model or something. For clinical data, you have some different models. I mean, I don't work in clinical data, so I wouldn't know what exactly specific models that you might find interesting. But the thing is that in each model you have parameters, and for each parameters you want to estimate them based on this based on a, like, if you want based on this Bayesian inference. Then you are trying to get samples using this MCMC, and just to get good samples you discard like the first bit of the samples. That's it. I mean, in practical, nothing changes. You also don't really need to learn. too much in order to how much warm up it should be. By default, if you keep the warm up to be half of the number of iterations, I think you like, at least for this stan HMC, I think it should be more than enough. Like you
Okay,
don't
it
need
will
to
be
think.
taken care. The model will automatically taken care.
Yeah,
Okay.
exactly. It's more automatic than you think.
Okay. Okay. Great. Great.
Yeah.
Yeah. Thank you. Thank you so much. And we have this cores and chains, right? So what's the
Yes.
difference between cores and chains?
The cores is basically how much CPU cores you have available in your machine. That's it. I mean, or how many you would like to use. So I mean, okay. So the number of chains is the number of Markov chains you would like to
Yes,
run for
yes.
your model, right?
Yeah.
So
Oh,
let's say you have some laptop that has 8 cores, and you would like like to use 4 cores to run these 4 chains. So you just simply say to Stan that please run the 4 chains distributed over four of these cores, and Stan would automatically run each of the chains like individually on these individual cores, and parallelly you would just get your result. That's it. If you did
okay.
not specify it, then you basically would, as I said, you would get it sequentially. So let's say each of these chains take, I don't know, like 1 minute. I mean, yeah, if it takes 1 minute, then if you don't have like multiple cores, you would take 4 minutes to complete the model. If you had multiple cores, it would take 1 minute because you specified the number of cores as number of chains.
Okay.
Yeah.
Okay. Okay. Thank you.
Yeah.
Yes, yes. Thank you. That makes sense.
Okay then. So if we don't have any question, then we can wrap up.
Okay.
Mm, no question, right? Okay. So yeah, thank you, Soham, once again for your wonderful session today. And
Pleasure.
thank you, audience, for joining us today. And we will come back again in the new year. So till then, keep learning art and keep learning our materials that is available in the YouTube channel. And yeah, thank you. So, and also wishing everyone Merry Christmas and Happy New Year. And we will come back again in the January with another exciting session on art.
Yeah. Thank you.
Okay. Thank you,
Thank you so
everyone.
much,
Bye.
everyone. Thank you.
Bye.
Bye. Yeah.